Okay, so welcome back to what should be the last video on Chapter 2. And again, we're looking at motion in one direction. And we have this example problem here. Very similar, in fact, it's got some of the same variables as the problems we've been looking at where we toss a tennis ball up into the air. But the difference here in this one is that instead of tossing the ball up and then allowing it to come back into our hand, we are going to toss it up and assume that we are standing on the edge of a cliff. Okay, and so we're going to toss it up in the air, and then instead of catching it, we're going to let it fall. We're going to let it fall, 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 fall all the way down to the bottom of this cliff, which is actually 50 meters below where it started. Okay, so oftentimes it'll be up to you to decide what point is, for instance, 0 and negative 50, or are we going to call the bottom of the canyon here 0 and the point we're standing at 50? You can make those calls for the most part, but since we already have a diagram here provided to us by the textbook author, and he's already chosen this as a starting point, we'll go with that. So we're going to say that where we launch the ball from initially, that is 0. We're going to go up to some height, which we previously calculated, and then it's going to fall all the way down to this point at negative 50. We want to know how long does it take the ball to reach the base of the cliff. So we're going to need to use one of those constant acceleration formulas, and we're going to want to choose one that obviously has time in it. So let me jump back to that slide and we'll take a look at our options. Okay, so here we are at the slide that has our constant acceleration formulas. This one's got time, and that's what we're trying to find out. How long is the ball in the air? But if we look at the other variables, there's acceleration, which we know. There's initial velocity, which we know, but then there's final velocity. We don't know that. We don't know how fast the ball is going to be traveling just before it hits the bottom of that canyon floor. So this is going to have two unknowns in it, so this is not the one we want. The other ones don't have time in it, so it's definitely going to be this one. X equals x naught plus v naught t plus 1/2 at squared. So let's write out that equation. X, or actually since we're talking vertical displacement, let's use y's instead. So we've got y equals y naught plus v naught t plus 1/2 at squared. So our initial, this is our final position, y is negative 50 meters down at the bottom of the canyon, equals our initial position, which was 0, plus our initial velocity was 15.0 meters per second up, multiplied by time, which we don't know, plus 1/2 times acceleration, which we do know because it's always negative 9.80 meters per second squared, and then multiplied again by our unknown quantity of time squared. So if we rearrange this, we have negative 1/2 times 9.880 meters per second squared t squared plus 15.0 meters per second t plus 50. This was a negative 50 on this side, but we want to bring it over to the other side of the equation with the other variables. Plus 50 meters equals 0. So what we have here is the quadratic formula. We have, we can simplify this. negative 1/2 times 9.8 is negative 4.9. Now, usually I try to encourage my students, and I try to do it myself, to write out all the units. But in this case, I'm going to drop the units out for now to focus on the algebra. Plus 15.0 t plus 50 equals 0. So we have the quadratic formula. We have ax squared plus bx plus c equals 0. So this is our a, negative 4.9. This is our b, 15.0. And this is our c. And our x's are actually t's, but that's okay. It's just the variable squared and just the variable by itself, and no variable at the end there. So like I said, this isn't an algebra class. I'm not requiring you to solve this by hand. And I don't know that there will be any questions involving the quadratic formula on the tests. So obviously you can't be using the internet or your cell phone on a test, but for homework problems, you can use whatever resources are available to you. And so I just Googled quadratic formula solver or quadratic formula calculator, and this is what I got. So calculator soup is what came up, and it will solve the quadratic formula for us. We just need to put in our a, b, and c coefficients, and it'll give us an answer. So for a, we've got negative 4.9. For b, we've got 15. And for c, we have 50. So we calculate, and it gives us two answers. Quadratic formulas typically have two solutions, and one of them is negative and one is positive. So we need to think to ourselves, which of these in the context of our problem makes sense? Well, what we're finding here is time, the amount of time spent in the air. So the negative doesn't work. That doesn't make sense, that we'd be going backwards in time. So it's got to be the positive 5.07 seconds. So our solution here is that t equals 5.07 seconds. Yeah, so the negative answer wouldn't make sense in this context. It's got to be the positive. And that's it. That's how long it takes for the ball to reach the bottom of the canyon. And so the last slide here that I want to talk about is graphical analysis of linear motion. This isn't a huge point of emphasis in the context of this class, although if you watch all the Khan Academy videos I have posted online to go along with these, they spend quite a bit more time focusing on a graphical representation of the data. So if we were to plot in an XY graph time along the horizontal axis and the relative position x along the vertical axis, what we find is that the slope of this line, where these data points intersect each other, to find the slope is rise over run, right? So we're finding the delta x over the delta t would give us the slope. So if the slope is delta x over delta t, does that seem familiar at all? What's delta x over delta t? That is velocity. So the slope of the graph represents the velocity of the moving object. So in this case, we have a constant velocity because the line has a constant slope. If we graphed position versus time, and it looked more like a curve, we can see that we are changing our velocity. That velocity is increasing or accelerating. And so in this case, what we're seeing here is a straight line, which indicates that the data being plotted here is from constant velocity. And the slope of the line equals the velocity. Okay, and then the final slide in the presentation here is an embedded video. Check this out. I'm not going to play it here because, like I said, playing a video inside a video doesn't make a lot of sense to me, but you can look at the PowerPoint I have posted to Blackboard and see this video. This, at the time, was the world record free fall. Since we've been dealing with free fall, it's just kind of a fun video to watch. Felix Baumgartner took this weather balloon up into essentially outer space above the atmosphere and jumped out of it, fell to Earth in free fall, eventually reached his terminal velocity, and then, of course, used a parachute to come to land. Pretty cool. Check it out. And that brings us to the end of Chapter 2. So, if you've got any questions, I encourage you to use the discussion board on Blackboard, and I'll see you next time for Chapter 3.